啊，应该也是 presentation。
我没有，啊，随便才行。你还上网也这样拿就了，那就到。
哦，
老师，你这
这样，
主要是我会做一点取舍，那个点，就是因为我都是来不及。
会我就会结会讲什
没有，
么？
我想问啊，就是他的现在也还好啦，就你刚教那个 chapter 6个或者是前面两个啊，虽然我读过了，所以不放心。跟 quiz 是不是差不多？
什么？
跟前两个 chapter 啊，
啊，
跟 quiz 是不是差不多？
差不多，全部都跟 quiz 差不多。
那我可不可以稍微认为，如果说不是 quiz 出现了，我可以没有那么重要
对呀、
？OK，
就算没有的话，我觉得你80多不会错。啦，应该都是一样的。
然后真的不解，我今天都会导致这个我猜的，
嗯。
然后我肚子痛，拜拜。是。
我还没有看到你的那个题目。Yeah，嗯，
Please 调人来 prove 这个是零嘛，是不是？不然如果我讲我上这个是进去的话，你上它也是零啊嘛。
也是可以，
然后我不
也是可以，
用做这个也是可以。
也是可以。OK。
谢谢老师。
你是说我算错是吗？
这个 y
嗯哼，
是这个嘛？
嗯
不然 fy 是这个嘛？Suppose 它应该是减8减24 y square 上。
应该是，应该是。
然后老师，我刚刚看那个题目有很多
这些
critical point，其实是要 based on 那个 picture 的，是不是？因为
讲讲，
好像那个
嗯
我找到这两个点，因为我
嗯
separate 的时候会找到这两个点，
嗯
但是这两个
嗯
点其实在里面是没有 critical point 的嘛。这样子我在考试的时候，我要确定我其实要画出这个东西，然后我才看两半，是吗？这题目我们那里做的时候，
嗯
我们会把这两个 critical point 算进来，
嗯，
然后加在一起的时候，我们要把这两个的那个consideration 丢掉，因为他们是
比其他的小，
它就是不是它是一个完整的弧形啊，就是因为这两个 connected 的，就是我看那个 explanation 是这样讲。
嗯
That's why，所以如果我们要做这样的题目，我们还要画答案出来。
可是你不是比较吗？
没有，因为有一个我看它的 explanation 呢，这个是就我新的 explanation 是这两个的 point，因为它不是 critical point，所以你要 explain 掉。
对啊，不是要其他。
可以给我看一下那个新闻？
我可以问你一个问题，
没问题。
对，简单。
那你会哦，12点了，12点了啊？
那个 volume 我看不懂题目哎，我是 subject volume，我都不还有找什么东西。
那个 Lagrange 的东西是吗？
啊
，Lagrange 的
啊
，Lagrange multiplier。
应该是吧？哎，不是，你的一个那边的，
integral 那边，
你叫我找一个 volume 和 subtraction to volume 走，我今天我都过完了，那你的 volume 都在，
要看一下哦。
然后再来。
嗯哼，
其实我们有我们其实这个 even like 这个是 small，but like 如果是那 in
我们 critical point 的问题。
在工程师的对。
可以。这样的话，我这个字又用错了，是不是？应该是 among 的3个点在某点。对啊，critical 不是包括这3个点，所以我应该是用错字，我应该说他们不是 extreme value。我要讲的它不是 extreme value，对，它是 critical，只是它不是 extreme value。这样我要改一下。OK。
这些土豆人，
你不熟吧啦？
操啊！不是啊，有点热了，语气都看不懂啊。
以前看不懂，这样不是整班看不懂啊？啊？
我要找什么？都不懂要找什么。有2个内容，一个
对。
啊。放在那边的，
啊，your friend。
放在那边的。
Okay, I think we should start. Before we start, right, I want to show you some animation here. So if you go to our Moodle page, right, there's a vector field animation. Okay, if you click into this vector field animation, you can try and type in some vector field and see how this vector field move, right? Again, for example, there's one of them we look at is minus yx. It's the rotating vector field. Okay. So if you follow the direction of the arrow and move. Huh? Okay. Yeah. So this will related to the idea we want to introduce later. Okay. How does the vector field rotate? Okay. How does it rotate? Rotate at the origin, and then the previous one, how it diverge from the origin. Okay, how it diverge from the origin. Whether it diverge or whether it diverge into the converge into the origin. Okay, so rotation and diverge. Later we will touch these. Okay. Okay. Remember this picture. Okay, so you should remember this as an example of gravitational field. Okay, everything get pulled to the center of gravity. Okay. Okay. Any question from last lecture or not? Have you tried the homework? The leftover lectures. Okay. Okay, so let's continue with Green's theorem. So what's Green's theorem? Huh? You need to start with what? Huh? You need a curve. What kind of curve? Simple. Okay, simple. And then close. Okay. And then positive oriented. Okay. And then piecewise smooth. Okay, good. So what is positive oriented again? Anti-clockwise. Okay, turn anti-clockwise. Good. So simple is no self-intersection. Close meaning is a loop. Piecewise smooth, smooth except at a few points. Okay, a finitely many points. So why do we need this simple closed curve? We need this curve to bound a region. Okay, bound a region. We call the region D. Okay, and then the curve is C. C is the boundary of my region. I put del D. Okay. So what's the result? Okay, if P and Q has continuous partial derivative, okay, what's the formula? What's the formula? The line integral is equal to the double integral. Okay, so what are the line integral and double integral here? Okay, so the line integral is evaluate around the curve. Okay, so this curve has orientation anti-clockwise. Okay, and then P dx plus Q dy equals to the double integral of Q will differentiate Q with respect to x, and then minus differentiate P with respect to y dA. Okay, so where's the one typical situation we apply this theorem here? We consider the P dx plus Q dx as some width done. Okay, some would done. Okay, would done around a closed curve. Okay, very important. Would done around a closed curve. Okay, would done around a closed curve. Okay, so you can see that why line integral become a double integral here. Okay, note that this line integral here, you are integrating a dot product. Okay, you are not just doing the usual one variable integral. Okay, you are doing the dot product. But on the right hand side here, you are doing the, remember, splitting the boxes into smaller and smaller when you integrate, do double integral. Correct? Remember or not? Remember the idea? This is the limit when you make your rectangle smaller and smaller and smaller, so that you can compute the volume. Right? Remember? Remember? Okay. Volume under the surface. Right? When you do double integral. Okay? Okay. Okay. Yeah, let's go on first. So let's do one more example. Okay. So evaluate this line integral. Okay, where C is the boundary of the semi and annular region D in the upper half plane between the circle x squared plus y squared equals to 1 and x squared plus y squared equals to 2. So this C, where's the C? C is the boundary of this semi-annular region. Okay, so this part here is C. Okay, so what's this notation here? Integrate and then put a circle. It's a closed loop. Okay, you integrate over a closed loop with positive orientation. Okay, so here is the positive orientation here. So so we can use well, okay, what you can do is you can use line integral, right? So you break this region into 1, 2, 3, 4. Okay, parameterize 4 curve and then do the integral. Works. By the way, last time the question, Ming work it out already. I posted last Sunday. Yeah, you can have a look in the lecture notes. Yeah, he posted out already. Yeah, so it's here. Yeah, you can have a look. It's on Moodle already. Okay. Yeah. Right. So you can go have a look on his calculation. Yeah. Yeah. So one way is you can use direct. So direct method. Okay. Parameterize. Maybe I call it C1, C2, C3, and C4. So parameterize. Use parameterized curves C1, C2, C3, and C4. Okay, and then do the line integral. Okay, you can do it this way. Or second way, we will do it today. So we use Green's theorem. Okay. So you can see that this C, what kind of region it bounds? It bounds a semi-annular region. Okay. Semi-annular region. So this is the D. The color orange is the region bound by C. Okay. So by Green's theorems, the line integral become a double integral on D. Okay. What's the function we need to differentiate over? Integrate over? Del Q. So what is Q in this case? 3xy over del x minus del y squared over del y. Okay, over dA. So So you see, this is the double integral over region D. So what have you learned in last chapter? How to integrate this? Have you done revision yet? How to integrate this? Polar. Okay, polar. So you use polar coordinate. Okay, what's the polar coordinate? How you rewrite this region in polar coordinate? Yeah, sure. Yeah, okay, that one is the change of variable. I equals to cos theta and y equals to r sine theta. Okay, so r from where to where? R from 1 to 2 or 4? Hey, don't play. Okay, so you are bounded by outer radius 2 and inner radius 1. Okay. Yeah, how about theta? 0 to pi. Okay, good. Okay, good. So, yeah, so let's rewrite this integral here. So let's turn our integral into r and theta. Let's put the d theta here. So any Jacobian or not? What's the Jacobian? R. Okay, good. Okay, very good. So the Jacobian is R. So what happened to the inside one? Inside one become 3y minus 2y, right? But we need to replace the y using radius and theta angle. Okay, so it becomes just r sine theta. Yeah. Okay. Yeah. Hi. Oh yeah, sure. So maybe I swap these then. Okay. Okay. So what do you get after integrating this? How to integrate this? You got sine, got theta, got r. You can split into product. Okay, I can split into product, right? Fubini's change order, but this one split into product. Okay. So we can split into product because the variable here doesn't depend on each other. Right? So we split into product. What? Yeah, so we split into theta portion, split into r portion. Because our domain here doesn't depend on r or theta, right? They are constant. Okay. So I can split my integral to this. Okay. Yeah. So what do you get in the end? Ishin, you finish? Huh? 14/3. Okay, you got 14/3. Yeah, check that you got 14/3. Okay. Yeah. Any question or not? Any question? No. Where's Zhang Yun? Injured Injured. Zhang Yun, huh? I mean Zhang Yun. Huh? Okay, so next, we says that Green's theorem apply to simple closed curve, right? Okay, and the region bounded by it. But can we apply this to region that having a hole? Okay, for example, I repeat okay, I complete the circle here. Okay, this annular circle. Can I apply Green's theorem to this kind of region or not? Okay, but there's a hole. Can. Okay, the answer is can. Okay, so how to do it? Yeah. Huh? Not quite. Like depend. Not quite. Okay. Depend on your function, right? Still depend on your function. Although your domain is symmetric, but how about your function is not symmetric over the domain? Yeah. Okay. So you need to have function symmetry on the domain also. Domain also have to be symmetric. Only you can split. Okay. So what can you do? Okay. So if you have some annular region, what can you do? You introduce two cut line. Okay. Introduce two cut line here. Okay. So if you cut like this, what does it mean? Okay. So I can split my D into D prime and D prime prime. So the top part and the bottom part. Okay. But what is my C now? Okay. Can you see what is my C? So my C will start from here. Okay. And then go around the curve and then comes in. Okay. And then go up and then go around and then comes in. Okay. Can you see that this curve here actually is the same curve outside? You see, can I pull these two parts up? Okay, so let me like this. So I can move like this, right? Then at the end, I will get back to what I started with. Imagine or not? Imagine. Okay, so I introduce this cut line here. I go up, follow the original C, and then come back another cut line, and then go up, and then follow the original C, and then come in again. So you can see that these two part, right? Okay, so let me draw. So this part, right? Wait. Yeah. Okay. Wait. So okay, I am not complete here. Wait. So let me start here. Okay, wait. What do you want? Wait. So you go from here, go up, and then go here, and then comes in, and then go up, and then comes here, and comes in. Yeah. Okay. Wait, let me think. So, use a rubber band to demonstrate this thing. What? I already drew for you. We go back. Okay, so what? Okay, wait. So what am I trying to say now? Yeah, so wait. Wait, you confuse me a little bit. Wait, let me think. What am I trying to do now? You confuse me a bit. Okay. Okay, let's start over. Wait, first. Okay, so the claim here is I can apply the Green's theorem to a region with a hole. Okay, so why we can apply a region that having a hole? So we need to understand this region as a single closed curve. Okay, as a single closed. So you need to understand this region as sums enclosed by some simple closed curve. Make sense or not? Make sense, huh? Like this makes sense, right? Okay. So how to do this? So we introduce two blue line here to cut. Okay, to cut our domain. Okay. So how this blue line works? So first we need to produce the new simple closed curve, right? Okay. So how to produce this new simple closed curve? So I think it's right. So like what Chie Sen said just now. So let's start with somewhere here, maybe. Okay, let's start with somewhere here. And then we follow the path given. Okay. So we follow here, and then we go up, and then we follow this path here, and then comes in, and then go out again, and then go over the original C, and then comes in, and then follow this path, and then close. Okay. So what you can see here is this is a simple closed curve. Yeah, the line intersect. So the line intersect here, right? They will cancel out. So here go in, here go out, here go in, here go out. So they cancel. The contribution cancel. Okay. So when you do the integral on this line, the contribution cancel out. Okay, because you have one line going to the left, one line going to the right. Okay, so they cancel out, right? Because over the same curve with different orientation, what's the relation? One is the negative of the other, but you want to add them out, so they cancel out. Okay. Yeah. Not simple, huh? The regions that are not simply connected. You mean why are they not simple? Huh? Yeah. Correct. Wait, let me think first. I think there's something going on here. Yeah, so I mean, okay. So the how do I say? Green's theorem said is if then, okay? If then. So if then can use the inequality. Okay, if not, doesn't mean then not. Okay, so P implies Q and not P implies not Q is different. Okay. Yeah, this one we'll see more in discrete math. Huh? Yeah. Maybe you also can start from here, right? So you also can start from here. Start from here. Yeah. You can start from anywhere actually. Just start from anywhere and then move with the cutting. Okay. So you note that this cutting here, right? We have to go left and right so that the contribution cancel out. Okay. Okay. If I think to get around with Hong-Ming's problem, right? Yeah. What are we really doing is we actually cut this into two parts. Yeah. Then join together is the same thing. Okay. Yeah. So we cut it into two parts. Also, like we need to integrate two parts. Yeah, integrate two parts. Correct. Integrate one or integrate two. I think depends on the question and the parametrization and so on. Maybe we do this. This one easier. Wait, which one? Huh? Wait. So if we split D into D prime and D prime prime, right? So these are two simple closed curves. Yeah. So there's no self-intersection here. Huh? Yeah. Okay. I think Zhe confused already. No. This one is new stuff. Okay. Let me restart again. Okay, go back again. So we have D, right? Okay, D is a semi-annular region. Okay. So what we do is we split. So we split D into two regions. Okay. So this is an annular region. So we split D into two semi-annular region. Okay, call it D prime and D prime prime. Make sense? Okay, how we split it with the blue horizontal curve or blue curve? Call it C1 and C2. Okay, C1 and C2. Is it okay? Okay, okay. So we plug it into C1 and C2. So if we want to do double integral on D, right? What do we do? Let's say we want to do it on this special function we had just now. Okay. So these two regions are what? Intersect at boundary. Okay, here boundary is the blue curve, right? So they intersect at this boundary here. Okay, so by the double integral property, we can split into two parts. Okay. D prime and D prime prime. Okay, I think this one is a proper explanation, because if I use the explanation just now, then you need to say why it also work for cross curve but not simple. But the explanation is exactly this, why we can use it in this case. Sorry? Yeah, because I'm integrating this special function over the region D. Yes. Yes. No. I mean, because we are interested in this kind of function now, so we try to look at this function on the domain. Okay. So why we can split? Because the region split into two, just intersect at the boundary, right? The boundary is the blue curve. Yeah. Okay or not? Yeah, this one is last chapter stuff. So if two, you can split into two regions intersect at boundary. Okay, so now we split into two regions that is bounded by simple closed curve. Right? Is it simple closed curve? Is it positive oriented or not? Simple closed curve, positive oriented. What else? Simple closed curve, positive oriented. One more is what? Positive oriented, simple closed curve. Piecewise smooth. Okay, piecewise smooth. Is it piecewise smooth? Yeah. So maybe except this 1, 2, 3, 4 point is not smooth. Maybe, not sure. But there are finitely many. Okay. So we can use the lines integral here. Okay, we can use line integral. So line integral here, let me write. So the first one, you go from where to where? You go from, okay, so how about we name the path? Above we name C, below, okay, C tilde 1 and C tilde 2, okay? So C is equal to C1 tilde union C2 tilde. Is it confusing or not? Yes. Yes. Okay. Let's rename the blue curve, okay? So just call it B1, B2 since they are blue. Then the outside one is still C1 and C2. C1 and C2. So we call the blue curve B. Okay? So so the first one, D1, okay? By Green's theorem, okay? By Green's theorem, because the curve is, the region is simply connected. Boundary is what? Boundary is C1 plus B1 plus B2. But before going to B2, we're still passing through one curve here. So how should we call this? So let's call it W, then W1 and W2 inside. Okay. So we go from W1, okay, and B and P, P dx plus Q dy. Okay. How about second one? Second one is what curve? Okay. So second one, we start with C2, go to B2, go to W2, go to B1. Okay, PDX plus QD. Okay, make sense or not? Make sense, huh? Okay, so you can see that this curve, right, also connected at the boundary. Boundary of a line is a point. Okay, connected at the boundary. So we can further split this. We can further split this. So we can further split the integral. So we split into C1 plus B1 plus W1 plus B2 plus C2 plus B2 plus W2 plus B1. Okay, and then the whole thing, I skip the function in the middle. Make sure you write. Make sure you write in every function in. Okay, but you can see that some of them cancel. Okay, which one cancel out? Huh? Which one cancel out? Okay, B1, B2 cancel out. So have we considered the orientation yet? Huh? What's the orientation? Let's fix the orientation for B1, okay? So the top one, we call it B1. The bottom one, we call it minus B1. Okay, don't want so many names already. Okay, just write negative so we know that it's a negative orientation. And then we fix the bottom one, negative B2. Okay. So let's fix our notation here. So for the second one, to match up the orientation for the curve, we should put C2 minus B1. Okay. And then W2 minus B1. Okay or not? Okay. Okay. Although they are the same curve, we take care of the orientation. Okay, we need to take care of the orientation so that we can join the loop together. Make sense or not? Okay, huh? Okay, so you can see that here we got minus B2 minus B1. Okay, so you can see that the B1, B2 cancel out. Okay or not? Can see or not? Why? Because integration of minus B2 equals to minus integrate of B2. Okay. Make sense? Can follow? Can follow? Okay. So what are these together? What are the leftover? So C1 B plus integrate W1 plus integrate C2 plus integrate W2. Okay. So it becomes integrate C1 union C2 plus integrate W1 union W2. Okay, so what are the direction of C1 and C2? So you see C1, C2 is also clockwise. W1, W2 is actually anti. Sorry, C1, C2 are anti-clockwise. W1, W2 are clockwise. Okay, so you can you see or not? Yeah, okay. So you need to remember that you need to make sure the outer one is anti-clockwise, inner one is clockwise, so that you can build the bridge and then they cancel out at the bridge. Okay. Okay. Make sense? Make sense? Make sense or not? Okay. Yeah. So if you want to make holes, okay, you want to make holes, right? You need to make sure all the curve around the hole is opposite orientation to the outside one, so that you can make this bridge. Make sense or not? Can I?
Like the whole curve, I don't want to cut the whole thing. I use the big one to minus small.
Big one minus the small one. Big one minus the small one.
So it's like the whole.
I know what you're saying, but is it correct or not? Feel like correct because I never did that. I never experienced. Yeah, I haven't tried that. Is it easier?
That's right.
No. I mean, wait. So actually, this is what you are doing, right? Actually, this is what you are doing, isn't it? This is what you are doing. Ne? The outer hall minus the inner hall, because minus of the clockwise become minus of the anti-clockwise become clockwise, right? Remember? Yeah, I feel like this is what you are doing actually. Yeah. Then the outer one minus the inner one. Because if you minus the anti-clockwise become clockwise, so plus a clockwise thing. Yeah, I think, yeah, good. Yeah, I think, yes, good. No, already tried. Yes. Yeah, good. I think very good. Yeah, good. Yeah, good. Yeah. Hey, come to MAT, yeah. Come to MAT. 房天. Okay. Okay, next. Let's see how to apply this. Okay. Let's see how to apply this. So let's say we have a function here. Okay. So you can see that what's this function actually? That's why I show you at the start, right? Minus y plus x. Minus yi plus x. So it's the rotate one. But you divide by the length. Okay, so you divide by the length. And then it's asked that show that the integral is 2 pi. Okay, for any positive oriented single closed path that enclose the origin. Okay, so you have this picture here. Okay, C is going anti-clockwise. C prime is going what? Going anti-clockwise as well. Okay, but just now if we want to apply Green's theorem to this, right, we need to turn the orientation in the inner circle, inner curve. Okay, so to be able to apply Green's theorem, what we need to do, we need to consider integration over C, okay, and integrate over minus C prime. Okay, only this we can use Green's theorem. Okay, only this we can use Green's theorem. So this is from just now. Okay, from just now. Okay, from just now. Okay, so I don't want you to waste time computing, so I just show you this partial derivative. If you have computer, you can check whether it's correct or not. So you get these two partial derivative. If you integrate differentiate P and Q. So what's the P and Q here referring to? Right. So here is referring to fxy equals to pi plus qj. Okay. So P is equals to minus y over x squared plus y squared. And then Q is equals to my x over squared plus. Okay. So you can see that this is actually 0. Okay, so they cancel out. Okay, so what to do? So what to do is we can see that if you integrate over the outer circle and inner circle, they are actually the same. Okay, they are actually the same. Yeah, so they are actually the same. So they are actually the same. Okay, so they are actually the same. So they are the same, but the answer say actually it's 2 pi. Okay, so how to get the 2 pi? Yeah, how to get the 2 pi? So how to get a 2 pi? How to get a 2 pi? Huh? And actually, just now we didn't mention why we consider this kind of region. You know why we consider this kind of region? Huh? So you see, this question is asking about any simple closed path that enclose the origin. Okay, so any simple closed path that enclose the origin. So why they want to throw away this origin? Because this function here will blow out at the origin. Okay, I'm not sure the limit exists or not, I haven't checked, but this function blow out at the origin. Blow out meaning at the origin the number shoot to infinity. Okay, right. Okay, so that's why they introduced this circle here. So this is a circle actually. So they introduced this circle here to avoid the origin. Okay, they do this integration. Yeah. What domain? Which one? Which one? 1, 2, 3. How to compute this? How to compute this? Yeah, I got P and Q and then yeah. What question is what? No, these two are the same function. Yeah. Okay. Okay. Okay, so we consider this circle here, right? So we consider any circle, okay? Maybe we can take this circle to, if you imagine we can take this circle to infinity, to 0, right? Okay, you can see that this D region here is approximating everything bounded by the region. Make sense or not? Make sense or not? If I reduce this circle some more and more and more, then this D here will fill up everything here. Not filling up, but taking limit. Remember the idea of limit? We keep approaching, but we never reach. Okay. Okay, this is the idea of limit. So, what we can do here is this outer C here is what we don't know. Okay, simple closed curve. But the inner C prime here is any radius we consider. Okay, we consider it as any radius. So the C prime here, what we take here is RT equals to A cos T, A sine T. So let's check whether the line integral depends on this curve or not. Does it depend on this A? Okay. Right. So let's check. Question. Okay. So we do this line integral here. Yes, I assign one. I pick any circle. I see whether this will affect the result or not. So we need to make sure that the A we choose is the circle is contained inside the closed path we pick. Okay. So let's compute this line integral here. So this line integral here is going from 0 to 2 pi. Okay. Of what? Okay. So what is P and Q? Okay, so this is P and Q. So if I will change this to polar coordinate, right, what happened? Bottom become R squared. Okay, good. So become R squared, bottom become R squared minus A. Okay, so in this case is A sine T over A squared, comma, A cos T over A squared. Okay. Dot product with R prime T. What is R prime T in this case? A minus A sine T, A cos T. Okay. So this is the tangent vector you need to take the dot product with. Okay. And then in the end, what do you get? So you get sine square T plus cos square T. Okay, can see or not? Because there are 2a at the numerator, 2a at the denominator, so they cancel out. Yeah, so you can see, what can you see here? So actually this integral here doesn't depend on the radius of the circle you take. Okay, all the a will cancel out, all the radius will cancel out. Okay, so what's this integral here? It's just 2 pi, right? Because the trigo identity we have is 2 pi. Okay, so the key, the important thing here is the outer C you don't know, just some simple closed curve. But you use the inner circle to compute it. Okay, make sense? Okay. Okay. Okay, so this one is by far the hardest example, I think, because this include everything you learn. Okay, can follow or not? And if don't understand, follow first, then try and think why we do this. Okay. Yes. Where's the C prime? This is C prime, huh? C prime is we fix one, okay? We fix as a circle. So this is we fix, okay? We fix a circle inside what? Inside the simple closed C. Again, closed curve C. So we fix the circle inside simple closed curve C. Okay. I'll assume one. I assume one. But we don't have this kind of hard question in the exam. Possible. Serious. Okay. Okay. What do you mean by put a square? You mean square outside here? Inside is you decide one, not me. If you decide a square, then you do a square. You're supposed to put 2 pi. Do you want to try that? You want to try that or not? I let you try it. You try it. So you put a square inside here, okay? Fix any length, okay? Fix any length. So square, four side, right? So you need to build 4 parameterized curve, okay? And then you write down the parameterized curve, okay? And then do for 4 part this thing. You should get 2 pi in the end. You want to try? You want to try? Huh? You will get the same one. Huh? Any shape also can. You want to try triangle also can. Maybe Q Guan Tian try triangle, then Hong Ming try square. One. Okay. And then you send me the solution. Okay. Yeah. Okay. 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 Next, we introduce this curl and divergence. Okay. Actually, let's come back to this formula here, Green's theorem. Okay. So this Green theorems here. Do you see why this one is so weird? Okay. Why we change position? Why we take negative? Do you remember what operation in linear algebra have this kind of property? You need to swap position and then introduce a negative. Cross product. Okay, cross product. So what kind of cross product we are taking here actually? Okay. So we are actually taking the cross product of what? D dx, d dy, okay, on PQ. Right? So let me write some more stuff, maybe you can remember. Okay, so what's this? Determinant. Okay, determinant. Cross product defined using determinant. Determinant AD minus BC, right? Okay, swap position and then introduce a minus. AB minus DC, correct? AB minus DC. Okay, so this is a dot product of gradient with the function. Okay, function we call it Gi plus Qj. Okay, so this is actually a operator here. Okay, gradient cross with f. Sorry, this is cross, not dot. There's another thing for dot. So cross with f. But what's the result here? What's the result on the left? You integrate over a line integral. Okay, you integrate over a line integral. So you calculate the work done that's done in a rotation motion. Make sense or not? Your line integral here. So if this line integral is non-zero, right? So meaning you have work done around the loop. Correct or not? Okay. So this value here, this cross product here, actually measure how the vector field rotates. Okay, on the xy plane, how it rotates. Okay, and then this integral here will calculate the work done by the rotation. Make sense or not? So this Green's theorem is very important to explain what's this weird thing here. What is the weird thing? What is this weird thing here? So you want to change positions to differentiate, and then you take the minus. Make sense or not? Definition what? Okay, so I mean, this is the physical interpretation for this cross product. Okay, does it make sense? Okay, make sense or not? Okay, so this is the work done around a circle, around a closed loop. Okay, so how do you have work done in a closed loop? You need to have something rotating, right? What's the thing that is rotating here? Is the vector field. Okay, so it's the vector field. It's rotating. Okay. Okay, vector field is the rotating. Okay, so here you see, here is a vector field. Okay, vector field. Here is the operator. Okay, so this operator add on this vector field tells you how much it rotates. Okay, how much it rotates. Okay, can or not? So let me ask you, what does the delta cross a vector field means? What's the definition of delta cross a vector field? Yeah. Okay, this is nebula. Okay, gradient. So let me. Yeah. Okay, so this is defined as a curl of a vector field. So let me write here. So curl of f, a vector field f. Yeah. Yeah, curl in English is also how curly is it? Yeah. Okay, how it rotate? Yeah, let me draw the xy plane. So how it rotate around the plane? Okay, so how does curl define? Okay, how does curl define? So you take the dot product of two vectors, a cross product of two vectors. Okay, first vector is the gradient. Okay, the gradient operator, and then you take the cross product with vector field. Yeah, do you guys know how to read this notation here? Don't know. Okay, so sorry. Yeah, right. So we can extend the definition to IJK and so on, right? We learn until IJK 3R3. Because that's a simple version of Green's theorem. I think the harder one is called Stock theorem, I guess. Later we'll see. Okay, Stock is a person. Okay. Hey, wait, by the way, do you know how to read this determinant definition or not? Okay. No. Huh? How to read? Okay, I explain. So, how to expand a determinant? Cofactor expansion, right? Okay. So what can you do is you can pick the top one expansion along a row. Okay. So plus minus plus, right? Plus. Okay. Then you need to multiply the minor here. Not already. Okay. To do the minor here, you do AD minus BC. Okay. And then second one, you have a minus sign. And then you take the minor. Okay. And then third one plus, and then you do a minor. I don't know what's the triangle method you are referring to. You mean like this and then get this? I don't know. Maybe we can discuss later. Okay. Okay. So let's try and compute this. Okay, try and compute this whether you can do the curl or not. I think to get the curl is quite important. See, you can compute the curl of the f. Okay, try and compute what's the curl of this function here. What's the curl of this function? Okay, so you differentiate x squared minus z squared with respect to y. Okay, minus differentiate. Formula sheet I thought I already released last time. Is it given or not? No, I released in the Moodle already. Oh, okay, okay. Yeah, can check it.
You forget already how to remember.
老师直接把封面系统给你们。
Release the scheme one paper inside.
Okay, try compute. What do you get in the end? Okay, see everyone can compute the curl or not? Hmm? You put IJK also can. Yeah. Put IJK also can. Everyone got this or not? Curl. Okay. Right, which one? Which one? Second one. You have a minus on the middle, right? Plus, minus, plus. Yeah. Okay. Check your answer correct or not. Check if you can apply the formula or not. When you all got the solution or not? OK 啊。
你今天还少一个风。
OK. OK. So you can see, what can you see here? What's this curve here? So this is a vector function, right? So you plug in different x, y, z, you get different vector. Okay. You put different x, y, z, you put different vector. Yeah. Okay. So next, the theorem is curl of a gradient is 0. Okay. Curl of a gradient is 0. So why is it curl of a gradient is 0? Maybe you can quickly write it down. So why is it curl of a gradient is 0? What are you doing actually? You are multiplying the gradient vector, gradient operator on the gradient. Okay, but what do you get? You get mixed. You get mixed partial derivative, right? So you see, del x, del y, and then del y, del x. But the Clairaut's theorem tells you that the mixed partial derivative should be equal if the function is continuous. Okay. Yeah, so they cancel out. Okay. So you get 0. So the mixed partial derivative cancel out. So you can write it out, the rest. Again, they are all 0. They are 0 by Clairaut's theorem. A mixed partial derivative equal. Okay. So why is this important? Why do we look at gradient of f? Gradient of f is a vector field. When does a vector field equal to gradient of f? Conservative, right? Okay. So this means what? If f is conservative, then curl f is 0. Okay. So this implies that if f is conservative, then curl f is 0. So in other words, what? Okay, if we want to check something is conservative or not, what should we check? Okay, so this is a logic. So just now we mentioned this logic. So P implies Q is logically equivalent to not Q implies not P. Okay. Okay. P implies Q is logically equivalent to not Q implies not P. Okay. This is called a contrapositive. So this means that you also can check if the curl, okay, the curl is non-zero, then F is conservative. Okay, so I give you another criteria to check whether something is conservative or not. It's not, so this is not conservative. Okay. Yeah. So if curl F is non-zero, then F is not conservative. Okay. Yeah, so this is the punchline. So if you compute the curl of the vector field is not 0, then the vector field is not conservative. Which one del Z, del Z? Del Z. Okay, this one del Z. Okay. Okay. Sorry. So the first statement is if f is conservative, then curl of f is 0, because I can write conservative vector field as a gradient of some scalar field, because curl of any gradient is 0. Huh? Make sense? Okay. So yeah. Okay, P implies Q, but P implies Q is not equivalent to not P implies not Q. Okay, but it's the swap contrapositive. Yeah, how many ways to prove? So one way to prove is you need to check. Okay, you mentioned about that one. So the last thing we learned last time is you check the partial derivative, right? How many partial derivative you need to check. So for 3 case, I think this encompasses everything. So for the 3 dimensional vector field, you need to check these 3 equations. Okay, you need to check this three equations here to check something is conservative or not. Okay. And then what else? F is gradient. F equal gradient. Or you straight away found the scalar field. Okay, you straight away found that it is a gradient of some scalar field, then it is conservative. But let's say it is hard to find the scalar field, then you straight away check the derivative of your vector field. Okay, check these 3 conditions here. Okay. So just now the one you check the curve. If the curve of your F is not 0, then it is not conservative. Okay, it doesn't tell you whether it's conservative or not, but it's not. Okay. And then what else? Also, conservative is equivalent to the line integral is independent of path, right? Okay. If F is conservative, then the line integral is independent of path. Remember the three condition here. There's a summary last time. Okay. Where is it? Yeah. So it's independent of path, and then any closed path you integrate, you get 0. Okay, for F conservative. Makes sense or not? Not make sense. Okay, now does it make sense? Every closed path is 0 because the curl is 0. If F is conservative, the curl is 0. Just now Green's theorem says if you integrate the curl 0, the line integral also 0. So that's why all the closed path is all 0. Make sense? Last time. I mean, yeah. I mean, get the statement first. Okay, get the statement right. What? Oh, the statement is so F is conservative is equivalent to what? The path integral is independent of path. Integral over closed path is 0. Okay? Any closed path is 0. Okay. So now after I introduce this curve, is it clear that y integral over all path is 0? First, if F is conservative, then the curve must be 0. So if it is conservative, there's no rotation. So if you integrate, if you do the Green's theorem, okay, you integrate the curve, correct or not? It's equivalent to integrate the line, the loop integral. Correct or not? Remember, and you need to have this in your mind. Must have this in your mind. You see, this is the integrate curve over a surface, and then this is a loop. Okay. Yeah. Okay. Okay. And you, yeah. Okay or not? Yeah. Okay. No. Okay. No, I mean, you don't understand, it's okay. But I have to get the statement right. What I say. Okay. You don't understand, never mind, but you have to get the statement right. Okay. For example, right? For example, okay, very easy example in your real life. Okay. Why red light must stop? The reason or not? Why? Why cannot blue light
stop? Why cannot green light stop? Why cannot yellow light stop?
It's a law.
Right? It's a law, correct? So you take this as a law. You remember this first. Later you will know. Okay. So everything you don't know, right? Take it as a law first. Okay. Yeah. It's just a convention. Okay. One reason is red light catch attention more than other light. Okay, let's continue this next time, okay? Okay, so yeah, anything you don't understand, right? Okay, you take it as a law first, okay? But most importantly is you listen carefully first. So let's take a break until 1:25, okay? 1:25.这个 F 是 vector field， 这个你看 F is a vector field， 这个小 F 是一个 scalar field。Next scalar field，scalar field 的意思就是说它是一个 R，n 去 R 的，
所以 R N
它的 core domain 是 R，因为 scalar 嘛 ，scalar field， 它的 core domain vector field 呢，它 core domain 是 Rn， 对不对？因为你的 gradient 是不是都乘出来过后不是一个 vector？gradient
乘出来过后是一个
gradient 是什么 del x del y del z 是一个 vector 所以你一个 vector 乘了你的 scalar field， 你拿出一个 vector， 所以
那什么这边直接这个等于 f x y z，
没有错吗？有错吗？
没有错啊，可是我不知道。
没有，它没有。
它这个 f 没有错啊，没有错啊，
没有，它这个 f 是已经被 define 了，它是 example 4 已经告诉你这是什么，所以你要去 example 4。
OK， 谢谢。
没什么，我找那个 proof 啊，
你找 proof 啊？
它就算这个 rectangle 的这个用这个 green string
对，没有错。
然后这样子。
没有错，没有错，没有错。
找到了。
你找到？对呀。可以，等一下可以大概说的啊，可以，我等一下先也讲大概说的。不用，我懂了。
懂了。
我懂了。因为是这个，因为刚才我们说的这个东西，对，这个东西就是这一个加上这个等于这个region。对吗？
可是它这个有算外面的。
对，我也有外面跟里面有，这两个，这个，但是我们 prove 了这两个加起来是0，所以是说这个 integral 等于点这个 integral 然后我们这个不懂吗？这个是随便的 symbol 好，但是这个是我选的，是一个圆圈呀，我要选那个 A such that。这个circle是躲在这个里面，我肯定能够找到这个。然后其实如果我们要真的找这个，就是这个 symbol code enclose the origin， 对不对？其实我们不是要整个都要填满，但是我们 skip 掉这个点，是因为这个点的时候它有可能会去 infinity， 应该是会去 infinity 啊，其实要 check 一下。这样的话它就爆了，就在这个点上面，所以我们一定要 skip 掉这个点。所以我们讲 skip 掉这个点，我们不要 integrate 那里点，所以我做一个圆圈。但是你的想法应该是，我应该要把这个圆圈越弄越小，慢慢填满它。但是我们算的时候 ，actually 那个 radius 其实没有关系啊。我们在算那个 integral 的时候，你管你用多小的圆圈，你都肯定是拿到 max angle。Max angle，
所以是
什么
f 是 conservative， 就是克就是0。
F conservative 它没有克没有 rotation， integrate 那个克过后就变成0了。
Stop， 慢慢来。等会是讲conservative。
conservative 代表它没有 rotation， 没有 rotation。
没有 ij，
没有克，没有克，跟 integrate close。integrate
constant。所以我
可以。
line
过来听
integral
他
of
讲，
curve 也是等于零。
听他讲。
因为它没有 IJK 嘛，就是一个好吧。
然后呢，
啊，你不明白，但是就是要抓那个 statement，先抓到那个 statement 了才开始讲为什么。不用到明白先，你先知道要做什么先。我知道你讲什么，我知道你讲什么，但是
到底有几个嘞？怎样多？我要晕了。
两个吧，不是，跟他红绿灯不对哦。
讲的是
要 confirm，要
按灯
summarize 你。
你讲的是你讲的是。
OK， 一开始我们学 conservative 的话 ，integrate over， 这个是 if and only if 啊，就是 integrate over any path， 它是 independent of path 的，所以全部答案是一样的，只要你两个点是一样的，管你怎么 path 它都是一样的。还有，如果你是 over 一个 closed path， 它的 integral 一定是0。OK，integrate over 这个 field。还有呢，就是 check 那个刚才讲了，如果你要 check whether 这个 vector field 是不是 conservative， 你就要 check 那个 equality del fe 那个啊，就是那三个啊，你懂我在讲哪三个吗？就是这三个，哪三个？呀，这三个呀，这个也是 if and only if，OK。但是我们最后那个学那个能够 check 它不 conservative， 如果科是不等于0，等它不 conservative，OK。如果它 conservative， 那个科一定是0啊。
可是要先知道它是 conservative
啊，那个要先知道，我已经知道，然后我还要做什么？是不是？因为问题是我要知道那个 f 到底不 conservative。
结束了。
conservative 的概念
啊
，conservative 的概念是什么？
你是讲 physics 的概念还是 definition？ 数学的 definition conservative 的话是那个 vector field 可以写成 gradient of 一个 scalar field 啊。physics 的话是这种 field 的话呢，它 conserve energy， 它的 potential， 它的 change in potential。
比如说从看里面 potential
啊，你就是想那个啊，对，
我明白。
那个是 physics， 那个是
integral
physics。
of curve 也是等于0，那这么我要 integral of curve？
没有。因为我们记得 conservative imply 全部 closed path 是0嘛，对不对 ？integral over 全部 closed path 是0。但是为什么那时候我们没有讲为什么是0吗？但是现在既然已经介绍了这个 Green's theorem， 又有那个科嘛，因为那个你科学那个科的话，那个科是0哦，像你 integrate 东西不是0哦，对吧？你这个没有这个 Green's theorem， 你要知道 Green's theorem 很重要是它是 integrate， 另一边是 integrate over loop， 另外一边是 integrate over surface。OK， 但是你 integrate 那个 curve over 那个 surface
会哪里？
去哪里？
over surface。
啊
因为你 integrate 那个用那个 surface 的 domain。
呀，再想一下，我再讲多一点，你再想一下。OK， 好，你看啊，你再想一下，等下再问。OK。Okay, so hello啊 hello。 Oh, okay, I want to provide you another way to think of this Green's theorem. Okay. Hello. Hey. Yeah. Hey. Steady. Okay. Hey, come back. Okay. So Green's theorems. So recall again, what's the statement of Green's theorem? Okay. Green's theorem says what? The loop integral is equivalent to the area integral. Okay. So why line integral and the area integral combine? Okay, like they are related. Wait, let me finish. Okay. So why? Okay. So like the technique we learned just now, you see, all this circle, right? Okay, all the circle here. We can make a lot of small circle. Okay, so you can see that if I make a big loop, okay, if I follow this big loop here, the inner path all cancel out.
Can imagine or not? Okay, cannot imagine. You see. So here you see here is going here. So okay, let's look at these two circles here, right? Okay. So let's say they are adjacent to each other. Okay. So this particular here is going to the right. Okay. If you look at the adjacent one, it's going to the left. So they cancel out. Okay. It's the idea we used just now. It makes sense or not? Okay. So you see, so you fill out the area using all the loops. Yeah. Then you make up the full line integral here. Okay. Yeah, adjacent one. Okay. Adjacent path they cancel out. Adjacent is type. Adjacent. Your neighbor is your adjacent. Tau is adjacent to you. Okay. Okay. So so what? Okay. So what? So you can see that here. Okay. What are you doing here? Okay. So this is a dot product between tangent vector with the force. Okay. Tangent vector with the force. Okay. So the left hand side here is tangent vector with a force. You integrate. Okay. But right hand side here is the curve. Okay. So the curve. Okay. Yeah. So this is integrate over a region. Okay. Region or region, you need to split like this region. Okay. And then you split further more and more and more and more. Because I didn't present you the proof, so this is just an idea. Okay. So you can see that if you split this region here, what are you doing? You are checking how curl is the vector field. Okay. No. This is the domain. This is the domain picture. This is domain. This is domain picture. All of them are domain. All are just domain. I didn't draw the vector field out. So vector field maybe if it is a gravity one like this one, right? Yeah, this is the vector field. You need to draw extra stuff if you want to. So on the left hand side here, you found the work done in clockwise position. Okay. So you found the work done in clockwise position. On the right hand side, how? Anti-clockwise, sorry. Anti-clockwise position. So how about the right hand side here? Okay. You're over area. Then what are you computing? Okay, what are you computing? Yeah, area. So area, how to compute the vector field? What's this? So you want to compute the work done in the rotational manner, then you need to integrate over the curve. How curve is it? How rotate? How much it rotate around an area? How much it rotate in an area? You fix the area. Yes. Yeah. Yeah. Okay. So over each point, how much it rotate? Okay, and then add up together. Okay. Yes. 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 This is talking about right hand side. Yeah. Yeah. Work done in the big area. Yeah, work done in the big area. Yeah. Okay. Because this is what you do on the left hand side, right? So you consider how all these small circle, how much work is done, and then add them up together, you get the large circle. Left hand side, I'm talking about left hand side. Okay, so this small green circle, right, is I break down the largest C here. Correct or not? Use the idea we used just now. The idea we used just now. So the half go to the left, go to the right, cancel out. So I combine all this circle here, all this anti-clockwise circle here to get the large anti-clockwise circle outside. Your question is like circular, you know, circular. We come back again. So why is it curve? Because this is a word done around a closed loop. So how you do word down around a closed loop? You need to rotate, right? You need to rotate the force. Right hand side here, right hand side. Okay, so you need to what is this integral here? This is an integral over area, right? Over area. So over area, what number you want to integrate? You need to integrate how curve is it, so that you will get. But depend on whether it is conservative or not. If it is not conservative, then it might not be zero. Okay. Okay. Okay or not? Yeah, a little bit. Is it not? Kind of. Yeah. According to that. Yeah. I also saw that. Yeah, according to that. Yeah.
Area or the whole area? Or both?
Area, whole area. What do you mean by that?
You see that one, man?
The
green color is the sub area.
Mm-hmm.
So the big area or the small area.
That one is fixed by you. So you fix what domain here? What domain you fix here, right? Depend on what domain you fix here. Okay. Yeah. So why I don't put why I don't put square instead of putting this area here? Because my surface maybe not rectangular, maybe a bit curved. So we need to use you need to use the Jacobian last time, right? Yeah. Right. That's the reason why we don't put dx dy here, because our area might not be just a rectangle or what, maybe a curved surface inside. Yeah, of course we combine. That's why the chapter is placed before this chapter, right? Yeah. Okay, so now what we do is we put vector field on the surface and then we compute that thing. Okay. Yeah. Okay. Okay, next. Okay, so determine whether this vector field is conservative or not. Okay, so what do you do? What can you do? Okay, you can use the equation or you can compute the curve. Okay, what's the curve of this? Yeah, cross product. So let's quickly do it. So what's the cross product of gradient vector with this function here? Okay, I think what's the first term? Calculate on the spot. What's the first term? Yeah, how to compute the J coordinate? This one. Okay, so what do you get? Okay. Yeah, so when you combine these two, what do you get? Negative 2y. And then plus or minus? Minus, okay, good. Okay, and then what's the middle one? Berwin, what's the middle term when you do curve? What do you get? Zero? Zero? So you want to compute the middle term, right? Okay, take the J. Okay, take the minor and then okay, so what do you get? What do you get? Minus x. But remember that the cofactor expansion will have a negative, right? So we put a negative outside. Okay, good. So how about the third one? Seng, what's the third one? Huh? YZ minus 0. Okay. So all together you get what? Minus 2y minus xy x and yz. Okay, so is this a zero function? No, right? Okay, so if you put different x, y, z, non-zero one, you will get non-zero. So this is not a zero function. So since the curl is not zero, then yeah, so since the curl of f is non-zero, f is not conservative. Okay. Okay. And next one, we skip on because it's similar. Checking conservative and then find potential. Okay, next. How to find potential? We showed it last time, right? So we have the gradient first, and then we solve integrate one by one, and then match up with the second equation. This is what we do last Friday. You have three, so you have three equations for your partial derivative, right? And then you integrate one of them. You start with integrating one of them, okay? And then you differentiate the answer you find and then make sure that agree to the second equation and so on. Forgot it. Yeah. Okay.
Or you just do the potential.
Just do what?
Do the potential.
Potential.
Do calculate.
Okay, so I mean, okay, so no. Okay, so to find potential, right? To find potential. Let's say if it is conservative, then only you start finding, right? If f is conservative. So you will get what? You get del f del x equals to f1, del f del y equals to f2, del f del z equals to f3, right? So what you do is you can integrate the first one first with respect to x. Right? And then you get something in terms of x, definitely, and plus some function in z and y. Okay? And then you differentiate this with respect to z or y. Okay? And then make sure that this agree with f2. Yeah. Yeah, to find potential. Huh? Yeah, find the original function. And then you go on. Okay, you go on. Okay, this one we did last Friday. Okay, if you don't remember, please refer to last Friday. And then you do until you satisfy all the equation you have. Okay. Okay, continue. So just now we take cross product, right, between gradient vector and vector field. We also can take dot product. Okay. If we take dot product, what do we get? Two vector. Yeah. So two vector we get dot together, we get a scalar. Okay, scalar. So this scalar or this function of scalar is we call the divergence. Okay, so there's a picture here.
So if the dot product here is always negative, then it is always going in. So you can imagine the gravity. Okay, if you compute this number here is always less than 0. If it is greater than 0, if this function is always greater than 0, then it is diverged from the origin. If it is equal to 0, then it goes somewhere else. No, it goes somewhere else. Like what you say, like parallel or something like that. Okay. Yeah, it neither. So the rate of going into this point and going up this point is the same. Skew is what, like this? Why is skew? I mean like this, like this. Like this, isn't it here? Or you mean here, like here, like here? Hey, next time I ask a proper question. Don't ask me to formulate your question, okay? Ask a proper question first. Think carefully first. Don't simply pause, okay? I mean, your problem is you are good. You are asking questions, but your question is you pause. Yeah, so it's you pause. So you need to every time check again the question that you want to ask. Okay. Okay. Yeah. So how about try and find the curl of this function here? Okay. Try and compute this divergence. What's this divergence here? What's this divergence? Huh? The what? Limit. What's limit? So what's the definition of convergence? So you take the gradient vector dot with the vector field. Okay. Okay, so Ziyi, what's the first term? The first term you get y 2xy z. Okay, good. Plus differentiate with respect to y 3x z cubed. Okay, plus or minus. Yeah. How about the other one? Last one. Negative 2z. Okay, good. Okay, so this is the divergence. So if you plug into the point, okay, you will get a number at each point, right? So if you plug a point in, you get number at each point. If it is always negative, then all the vector is pointing inward to the origin. If it is always positive, then upward. Okay. Diverge, whether it diverge at a point or not. Okay, at a point. Yeah, so this one is the other way around, right? So I mean, diverge is like this, right? Okay, the opposite of diverge is converge. Yeah. So when it is equal to 0, you can look at this point. The rate of going in and out is the same. Yeah. So if you go in, also like this, go out, also like this. Okay. No conclusive here. This is just some pattern. Yeah. I haven't defined diverge also. This one is just a concept, idea. Which one? You mean this point, this thing? This thing depend on x, y, z, right? This one depend on x, y, z. It is not always 0 or less than 0. Yeah, you need to. Huh? You need to bound it. You need to bound it. No, I mean you put different x, y, z. This number is either positive, negative, or 0.
No. There's no converge or divergence here. So this is just an idea of a divergence of a vector field. Okay. If diverge is this kind of picture, and then if it's not diverging, sometimes it's converge, or sometimes it just flow through it. Yeah. Yeah. Or just pass through. You can think like that. Yeah, because we didn't define what's converging. Huh? Yeah. Hey, okay, I know why you guys so many questions. You know why? Because you don't listen to me. Because you put your own idea. Okay, everyone got their own idea, right? So make sure you listen to me first before you ask questions. Okay. So everyone must listen to me first. Okay. Listen to me first, before you put your own idea. Okay. Ask based on what I say. Okay. So what do you mean by same direction? Okay, I say, what I say just now is the rate going in and going out. There's a what? Yeah, okay, I haven't finished yet. Okay, so over a point, there's something that flow in and flow out. Okay, so when it is equal to 0. Something flowing in and flowing out. If it is greater than 0, then it keeps flowing out. So this thing, sometimes we call this is a source. Okay, this is a source. So you are source. So you give up. And then this one is called a, what do you think? Sink. Okay, this is sink. So you water going to the sink, right? All the water going to the sink. Okay. This one, this one no name, just bypass only. Okay. Okay, okay, yeah. No. This is the idea help. No, this is the idea help you imagine the dot product. Cost product, how it rotate around a point, the curve. Okay. Yeah. Okay. What? Yeah, this vector calculus is kind of difficult. Yeah. Okay. So next. Hello. Come back. Hello. Okay. So last time we have a curve inside our space, right? Okay. We parameterize using one variable. Okay. So if you got a surface, how many variable you need to parameterize it? 2. Okay. So it's 2. So if you have a surface, okay, if you have a surface, how many parameters? Huh? iPad start. Hey, yeah, correct. So wait. Okay, so you see, so you have a curve, right? You parameterize with a t. Okay, if you have a surface, you parameterize with 2 variables. Okay, because you need to go at least 2 directions. Yeah. Okay, so this is the next part. So we generalize the parameterized idea to surface. So we go to surface here. Okay, so this surface, we see the surface in 3D. Okay, so there are 3 positions here. Same like curve. Curve also has ST, YT, ZT. All right. Now you have XUV, YUV, ZUV. SUV. Okay. Okay, next time I will set CRP. It's okay. Okay, it's okay. Okay, parametric curve. Okay, so let's see an example here. Okay, so if we parameterize our curve as 2 cos u v and 2 sin u, what do you think? What is this curve is? What's the surface is?
cylinder. Why is it cylinder? Because the third and the first coordinate satisfy a square equation. Circle equation. Okay, circle equation. Okay, so 2 cos u squared plus 2 sine u squared is what? 4 is 4. Hey, wait. 4, right? Yeah. Don't confuse me. Okay, so it's 4. Okay, so the first and the third satisfy a circle equation. How about the v? V is the extra condition. So it's the height. Okay, so you got a circle and the x z plane, and then every v you got a circle. So altogether you got a cylinder. Make sense? I think this is a bit revising what we did last time already. This is what we did. Yeah, in the second topic, I think. Second topic. We also got do surface a little bit. Which one? Yeah, now got 2 variable here, u and v. Okay. Yeah, so v doesn't change, doesn't depend on u. Okay, v doesn't depend on you. Okay, y doesn't depend on you. So you have 2 variable here. Okay, can or not? So the first and second are both in terms of u, so they can combine. Okay, make sense? Yeah, question?
如果今天那个 J
啊
那边是 U 这样
it's just a line. So it's just, remember some last time we talked about this? Yeah. Yeah, last time we talked about this shape, right? Yeah, last time we talked about this shape. Yeah. So if everything only in U, then only one variable, that means just a line. What line is it? Yeah, you need to check. Yeah, spiral. This one we discussed last time. Okay, okay, next, just go through again how to find this parametric curve for this plane. Okay, what is this? Okay, so to build a plane, right? Okay, to build a plane, you need two lines which are not scalar multiple of each other, right? If you use 2 lines that are scalar multiple of each other, you just get a line. Okay, so as long as there are 2 non-scalar multiple of each other, so especially you can take this B and A. In particular, you can take the B and A. Okay, you can use this B and A. Okay, so how to write down this surface here? Okay, you want to use 2 variables here. Okay, so you need to take all the combination of the 2 lines. So U times A plus V times B. Okay. Okay, so this one you make out a plane. You take the linear combination. Okay, take the linear combination of these 2 lines. Okay, you can build the plane. But you need to make sure that this plane contains the point you want. Okay, what's the point you want here? P naught. Okay, you need to make sure that P naught is on your plane. Okay, P naught is on your plane. So how to write all these in the X, Y, Z variable? So you need to let your P naught be some X naught, Y naught, and Z naught. Okay. Also, your A and B, what are they? You need to write in as a A1, A2, A in a vector form. Okay, and then B1, B2, and B3. Okay, make sense or not? It makes sense or not? Huh? See, this one I already mentioned before I start, right? So what did I say when I start? Line, Y got S, Y, Z. Y got S, T, Y, T, Z. Where is my line living in? 3D. So where's my surface living in? 3D. And so that's how we got X, Y, Z. Yeah? Listen, okay. Okay, so altogether, what can you do? You can write everything in the X, Y, Z form. So this is a vector function, right? How to write a parametric equation? How to write parametric equation? Yeah, X, Y, Z. So how to write? AU, A1, U1 plus B1, V plus X0. Yeah, also can. All can. All can. Plus is commutative, so it's okay. Okay, so how about UVA? 依照 why not plus UN2 plus VB2. Yeah, okay, and so on. Okay, so this is, so the first one is called the vector equation. Remember, I just recall the second one is called a parametric equation. Okay, yeah, repeat what we do last time. Recall. Okay, so this one is Z0 plus U A3 plus B. Right, because the first one looks like a vector, right? You gave a vector, sum of vector. Second one, why is it parametric equation? Because these x, y, z are parameter, okay, and then they are all equation, parametric equation. Okay. Okay, okay, so far so good. All right. So how about sphere? How about sphere? X squared plus y squared plus z squared equals to a squared. What about sphere? This is the radius. How many radius? What's the radius of the sphere here? Radius of the sphere. A. A is the radius. Okay. So you see, there's S, Y, Z here. How to use two variables to control this sphere? How to use two variables? What are the two variables you need to control this sphere? Theta and phi. Okay. So how do you use theta and phi here? What's the spherical? What's the spherical? What's the coordinate names? Okay, you need to use the spherical coordinates. Okay, x equals to a sine what? A sine phi cos theta. Y equals to a sine phi sine theta. Z equals to a cos phi. Okay, phi is going from where to where? 0 to pi. Theta is going from 0 to 2 pi. Okay, then what do you do? So this is just the spherical coordinate. A sine theta cos theta, comma A sine theta sine phi sine theta. What? What's going on?
会下雨过后风景比较好，风景比较美。
Hey, okay. So you see. Okay, so you see, there's A, phi, and theta. Why there's only two variables we consider phi and theta? You know why? 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 Why we just say there's phi and theta here? Because A is the radius, it's fixed already. It's a particular A. Okay, so A is fixed. So here, A is
a fixed number. Okay. So for example, you can think of this A equals to 2. Yeah. So it's a fixed number. Okay. Yeah. So meaning if I give you any radius, right? If I give you any radius A, you just sub your A inside here, then you get your parametric equation. Make sense or not? Okay. Okay. Yeah. So for example, so let me write here, for example, so for x squared plus y squared plus z squared equals to 4, the parametric equation is 2 sine phi cos theta, 2 sine phi sine theta, and 2 cos phi. Okay, yeah. Yeah, so this is an example. Presentation. Okay. 我做校长先给。
不可以啊。
OK，等你孩子出来。OK。Okay. So. Okay. Next. Okay, so we skip this example here. So let's continue. Next is the tangent plane. Okay. So we have a surface. We have to study a tangent plane. So this is chapter 14 stuff. So how to get a tangent plane? What you do is you partial differentiate with respect to the two variables. Okay. If you use uv, you partial differentiate with respect to uv. If you use phi theta, you partial differentiate with respect to phi theta. Right? Okay. All right. So suppose you have this general equation for parametric surface. Okay. So what you do is you partial differentiate with respect to u, partial differentiate with respect to v. Okay. So you get what we call the r with respect to u and r differentiate with respect to v. So you get these two tangent vector. Okay. So how to find the tangent plane? Do you remember or not? Just use these two vectors to build the tangent plane. Okay, it's the same last time. Okay, so here. Okay, so what is it here? So if you have these two tangent vector, right? When they dot together, cross together, what do you get? Remember or not? Revision for chapter 14. If you cross product of two tangent vector, okay, on your surface, what do you get? You get a normal vector. What's that normal vector represent? It's a normal vector to the tangent plane. Okay, it's a normal vector to the tangent plane. Okay, so there's a proposition here. So if the dot product is non-zero, okay, it's always non-zero. That means the surface is smooth. Okay, the surface is smooth. There's no corner. Okay, so for any smooth curved surface, you will get a tangent plane that contains the tangent vector. Okay, and then the cross product is the normal vector. Let me see. Okay. You want to do this equation of tangent vector or not? Revision. As a revision. Want to do? Do. Break. What time is it? 2:07. Okay, we do this and then we break. Okay, we do this and then we break. I already said do this and then break. Then you ask me can do first or not?
Okay, do this first. Okay, so you want to find tangent of tangent plane, right? Tangent plane. What procedure you can use? You want to find plane. What do you need? Normal vector. Okay, how to get normal vector here? Yeah, what's the two thing you need to cross product? Partial. Okay, you look at the two tangent vector. Okay, two tangent vector, RU and RV. Okay, so if you partial differentiate with respect to u, what do you get? To u 0 and 1. With respect to v, 0, 2v and 2. Okay, so you cross product these two, what's the vector you get? Yeah, normal vector. So what's the vector in this case? Yeah, minus 2v minus 4u and then 4u v. Okay, good. So this is the normal vector. So you got a normal vector. You want to find plane. What else do you need? You need a point. Okay, what's the point you have on this plane here? 1, 1, 3. Okay, you have the point 1, 1, 3. So the equation is what? This one must ask Hong Ming how to find the equation of a plane. How to find equation of a plane? Already got point, got normal vector already. So how to put together? What equation? Ah. C naught by C naught. Okay, equals 0. Okay, so what's our A naught? So our A naught, B naught, C naught here is 1, 1, 3. So you just put everything together. Okay. Of course, you should evaluate your normal vector at 1, 1, 3, right? Okay, so you need to evaluate your normal vector at 1, 1, 3. Evaluate at 1, 1, 3. Okay, so 1, 1, 3. But your normal vector here is u and v. How to find it? You have to sub in into your RUV. But your RUV is u squared. Sorry, let me see. RUV is u squared v squared u plus 2v. Okay, you want this to equals to 113. So what are the answer? Yeah. So u could be what plus minus 1, v could be plus minus 1, but how could it be u plus 2v equals to 3? U and v must be 1. Okay, yeah. So this implies that u equals to v equals to 1. Yeah, so at u equals to 1, v equals to 1, we got the vector minus 2, minus 4, and okay, so this is how I get my ABC. What do you mean? Doesn't matter. You remember why doesn't matter? Because if I put minus everywhere, I can remove it also. Same equation. It's really the same equation. Which thing? That one is line. That one is line. This one is plane. So later we will see. Later we'll see. Yeah, later we'll see. We got, but the same, but it's the same line equation. Same plane equation. Yeah, same plane equation. If you like, right? If you like, I also can write like this, right? Yeah, if you like, you also can write like this. But how to determine whether it's go up or go down? Later we'll see. It is send the line. A bit different.
Okay lah, let me tell you now lah, spoiler. Okay, how to decide orientation of a surface? Okay, you see the k variable or the z variable. If the z vector is positive, then go up. Negative, then go down. Okay, so this is the way that differentiate up or down. Okay, only look at the z. Okay, going up or going down.
So in exam, do I need to expand the equation? I can just remain like that.
What else you want to explain?
Multiply inside.
What do you mean? Oh, you mean expand the you can leave as both this one enough, this one enough. This is enough.
So if I explain it wrongly, I will know marks, right? I get marks.
Okay, yeah. Right. Yeah, right. Okay, let's take a break until 2-0. Okay, 2-2-0. Take a break. No, plane is the same, but the normal vector going up or going down. Okay, going up, then the k is positive. Going down, the k is negative. Normal vector. Surface you won't change, right? So over a surface you got a normal vector, right? So you eat the loop or the satay, right? So you stick to the normal vector. Correct or not? Okay, so either you go up or either you go down. Okay, if you go up, the k is positive. Go down, the k is negative. Huh? What do you mean? Huh? So here, here is what? Here is going positive. Positive. Yeah. So when it's positive, we say it's outward. Negative, inward. Okay, only also over a surface, right? Give me a surface. So this surface, right, only have one outward, one inward. Go in or go out. Go in or go out. Okay, outward or inward. Okay, k is negative, then inward. K is positive, then outward. Outward. Okay. Okay,
差一点被绕走，差一点啊。原子弹为什么叫原子弹？一直圆。
你要先听我讲，你没有自己的想法讲。
没有想法，没有想法。
问你啊，
跟他讲换地方了。
一直不知道找
OK， 这个启示这启示不是，它这个启示是要找，你看，它是讲全部的 oriented closed curve。OK， 它算是图牌，但是问题是这个圈不是single closed curve 嘛，对不对？所以我们可以用那个Green's theorem 哦。但是如果用 Green's theorem 的话，这个 region 里面包含一个点叫做 origin 但是在这个 origin 上面，这个东西是会去 infinity 的。OK 很大很大，因为如果你做那个 L'Hopital 的话，你就会看
哪一个东西必须很大？
就是这个 function 本身因为我要 integrate 这个 function。然后做什么呢 ？And then 什么 ？And then， 所以我就要 avoid 这个点哦。OK， 我怎么 avoid 这个点呢？我就avoid， 我就做了这个圈在里面，我要 avoid 这个点。
就是把那个用那个圈，
把那个点丢掉，把那个点丢掉，我不 integrate over 这个地方，对吗 ？OK， 呀、然后呢？问题是，如果我加了这个点，这个圈过后，我还可以用 Green's theorem 吗？可以， 因为我刚才前面要拆成2个，对，跑到哪去了？
它弄成 simple。
对，变成2个 simple 的 simple cross curve， 对 ，OK， 就用刚才那个这个方法来拆，所以拆了过后呢，你拿到什么呢？这个 part 这边这个 part 其实是0，这个 part 是 Green's theorem 的那一个 part， 那个 double integral 是0 ，OK， 但是另外一边呢，它是2个 line integral 组合的。我 integrate over 外面这一圈等于 integrate 我里面这一圈 ，OK？ 但是这个里面这一圈是你选的哦，像你选一个东西你可以控制的啦，是不是？我就选一个 circle 容易 parametrize 吗 ？OK？ 我就选一个 circle 咯，然后我选这个 circle， 你可能要问我要选多大的 circle，OK？ 我就选一个躲在这个 simple cross 里面的 circle， 肯定能的嘛 ，OK？ 你就找一个小的 A 就好了 ，OK？是不是可以这样讲 ？OK， 然后怎么讲呢？如果你要找完全部的话，找完这个整个 region 的话，你是不是要让这个圆圈越小越好？所以你要看它的 limit 嘛，对不对？越来越小，越来越小，看到它去哪里。但是 turns out 我们算出来的这东西呢，不 depend on 它的 radius。OK， 所以我们算一个来看一下它是什么东西。我算出来看一下，哦，原来那个 A 哦在里面的时候它 cancel 掉了。没有影响，然后你算出来是2派，所以意思说，不管你拿什么 radius 在里面呢，它都是这个2派。
2派是什么
？2派就是那个 line integral， 就是这一圈的 line integral， 就是这个 vector field 在这一圈 loop 上面做的工作是2派。
我没有被这个里面的影响，对不对？
它是
里面那个算外面的那个东西也没有被外面的，也没有被里面的影响
里面来算外面，
没有错。Yes， 你肯定不懂，因为你没有听前面。
哪一个？听前面哪一个？
没有。
中文懂，我没有听前面的。
你都不在这里，你能够听到你是顺风耳
啊？哪一个？我刚刚上次
没有，他问不一样的东西。
我想问，这样子这个跟这个其实有分别的嘛？
这是啥？
这个
这是 del f，and then 呢？
跟这个我们算的这个东西也是找两边的。
directional derivative，
no， 这不 directional derivative，
U 啊，
不一样，这个是 scalar field， 这个 r 是一个 vector function， 所以是一个 vector field。
哦，所以这个是 scalar field， 这个是 vector field。
没有，这个
r
这个 r 跟这个 f 长得不一样。怎么？你这么忽然间拿一个东的东西来跟我讲西的？这2个要有靠近的东西，你才可以跟我问我是不一样的西的。你不可以拿一粒西瓜来问我这个 orange 嘛，对不对？这个到底跟它有什么关系？造成你觉得它们一样？先跟我讲先。
也是说，
我也不知道这个 u 是什么东西。
unit vector，
那个这是 derivative function。
对，一开始在那个
没有 change。
像你 del f 乘了这个东西是什么东西呢
direction 那个 gradient 呢？
怎么要这样呢 ？del f 本身就有，其实不是，你知道吗？你这个是东西，你知道是什么吗？
不是很懂，为什么算？
耶，
对。你还记得什么是 exact differential equation？
好像
它就是跟 observative 好像有关系。
有关系，好像有关系，好像有关系，好像有关系。这个 u 跟这个有关系吗？怎么来的？这个从哪里来的？
这个前面来的。
前面是哪里？我好像没有印象。
那边
也没有印象啊，有这个东西咩？
有那个 unit vector 我记得。
有 directional
derivative duf。
可是我们通常你是讲它 length one 这个东西是这个，这是它OK， 像这个是什么呢？
所以我们这是
这是什么呢？这个是这个这样就通了。这个是这个 ，and then 这个是，等一下你再给我想一下，讲的怪哦。
有一个比不是
不可以这样讲，不可以这样讲。 因为这个是一个 scalar view 来的，但是这个是那个 curve 或者 surface， 这东西是叫做 tangent vector， 这是 tangent
这
vector，
个不算 tangent， 也不算 tangent，
这个不算，这个叫做 gradient， 这叫 gradient， 然后这个东西叫做 slope 啊。到 higher dimension 的时候就不太一样了。在 one variable 这些全部是一种东西。
对呀对呀。
但是上去的时候就不一样了。我们教的名字是不一样的。
对的吗？这 supposedly 是 tangent line 的 line at in direction of you 吗？
就是它的 curve 啦，上面有一个 tangent
啊，可是
跟这个有什么分别？这个也是这个样子吗？不是，也是gradient 也是在一个线里面它一直换的 gradient 吗？
是我慢一点再跟你讲这个东西，这个东西有一点 involve， 我会跟你讲，我可以跟你讲，可是不是现在。慢一点再跟你讲。
这个是要做 cross product， 这个做 dot product 我就找到了。有没有做 cross product？
我这是在找 normal vector， 你要知道要找什么，你不可以只看我在做什么，你要看我要什么先。我要了什么我才做什么，不是我要做什么我才拿什么，你懂吗？不是因为你做了才你要，是你要了你才做。
还要 gradient of normal vector
啊，不，我要 normal vector， 不是 gradient of normal， 我要 normal vector。
这题目我没有大家所以没有他的那个题目。
跟紧，就是你要知道我要什么先，要了才做。不是做了才。
就是还有
OK，
要 normal。
你就看你一定要找 normal vector 吗？你要找配你要 normal vector 吗？因为你现在你找出来了 R 这个3个。
Okay, let's come back. Okay. Next, I'm not sure you remember when we introduced the cross product, right? Yeah, when we introduced the cross product, we use it to find the area of the parallelogram. Remember or not? Okay. So how to find the parallelogram, the area? So we use the B sine theta times A. Okay. But what is this? What is this? So if they become a vector, what happened? If it becomes a vector, what do you do? Okay, what you take is really the length of A and length of B. Okay, and then what is this formula here? This formula here is actually the length of A cross B. Okay, yeah. So if like just now we take two tangent vector, cross them together, we get a normal vector. Okay, this normal vector represents the area of the plane. Okay, area of the plane. Okay, area of the plane. So this is the formula here. Okay, so you have a surface. Okay, you suppose you have a parameterized surface here. Okay, and then you find your tangent vector with respect to u and v. Okay, and then you integrate the length of this normal vector. You will get the surface of area formula. Okay, so this one you can briefly see. Okay, I won't prove it. Okay, maybe we are not using it, but we'll be using it as a Jacobian later. Okay, yeah, as a Jacobian. So this is how the Jacobian come from. Okay, why we have the J? Okay, the J there is actually this thing here, area of the parallelogram or the square. Okay, yeah, okay. Yeah, the Jacobian is this identity, this quantity here. Okay. So if you have a specific form of surface, okay, z equals to fxy, then you can write the formula like this. Okay, 1 plus del z over del x square plus del z over del y square. Okay. Okay. So just now, okay. So let's compare these two, right? So the first one, we have this surface here, written in this form, okay, written in UV form. UV. Okay. And then the area of the surface is given by the length of my normal vector. Okay, you remember the area of parallelogram. Okay, yeah. So this is the formula for general parametrized surface or parametrized surface. Okay, but if you can write your surface in terms of z equals to xy, fxy, then you just use this formula here. Okay, so you can derive. Okay, we won't derive this. Okay, so these are why we need this because this is exactly like the line integral. Can you see that this is similar to line integral? So we have first we introduce the arc length formula, right? Square root del what? Del z del x square del z del y square. Okay, that is just compute the length. But then how to introduce the line integral? Over the point we have the function, weight function. Similar to here, we need to start from calculate the surface area first. And then over the point, we put function. Okay, so now I tell you how to compute the surface area first. After we know the surface area, and then we put weight on the top. Okay, every point got how many value at the top. Make sense or not? And then we will get the volume over the surface. Can or not? You know? Example, huh? Okay, let's see example. Let's see example. So next we will introduce this surface integral. Okay, so how to imagine surface integral? You need to start with the line integral. Okay, line integral we have line in R2, and then we have function over the line. So we are getting the area of the curtain or the fence, right? But now the domain line become a surface. Imagine or not? Imagine the line draw out a surface. Okay. Yes. Wait. Let me draw for you. Let me draw for you. Wait. Be patient. Yeah, be patient. Okay, be patient. So we got the line on the domain, right? Okay, and then we have function above it, and then we get the line integral. Make sense or not? Okay, now we no longer consider line anymore. We consider surface. Okay, we consider surface like this. Okay, use the line, draw out the surface like this, maybe. Okay, and then we need to consider everything above the surface. Okay, need to consider everything above the surface. Make sense or not? Okay, can make sense? The domain become a surface. Anything? Just a surface. You integrate over a surface. Okay, this one depend on how you imagine. What I imagine is like you start with this string here, then this string can propagate through the space, right? And then every trajectory here, if you combine them, it become a sheet. Not shit, it's a sheet. Okay. Actually, they call this a world sheet. Yeah, the world sheet. Okay. So the world is a. Huh? What? What do you mean by? What do you mean by stack work? Oh yeah. I mean, there's a function above this surface, and then you integrate. If you take the surface integral, is we taking the volume under this function. Okay. Okay or not? I think you guys are quite think other things already. You don't follow me. Please follow me. You gonna use the shampoo or not? Follow me. Follow me. Wait. Okay. Sorry. Wait. And then one more thing. This surface here, right? Not necessarily live on R2. Okay, it could be some sphere like this. Okay, it could be some sphere. And then I look at a surface integral over the sphere, also can. Okay, so this is the hard part of our surface integral here. Okay, so the surface could be something else, not just a plane. Okay, it could be a sphere. Okay, something moving in the 3D. And then above this thing, what's the function? Okay, then you integrate over the volume over the surface. Understand or not? Okay. Okay, so let's go to the real definition here. Time is it 233? Okay. Surface integral. So you need to start with a parametrized surface. That's why we introduced the parametrized surface first. Okay. What you do? Same. Okay. You split your surface by rectangle. Make it smaller and smaller and smaller and smaller. And then look at the height. Okay. It's the same idea. But now your plane, your surface here is no longer plane. Okay. It is something like this. Okay. Something living in 3D. Can curve one. Okay, you guys are closer to this computing astronomy stuff already. So you have a curve. You see your surface is something in 3D. Okay, no longer in R2 anymore, in 3D. So you see this surface will be curved a bit. How to calculate the curvature of this thing? Okay, what you use? You use the tangent vector, right? Just how we use the tangent vector. Correct or not? We use a tangent vector to make this circle into the real circle that you know how to compute. Correct or not? Okay. This is the idea. We don't go deep just now. So this is basically what this is doing. So you have a curve. You have a curve square. Okay. But you can calculate the area of this curve space just by using the tangent vector. Okay. So this is what this RU cross RV is doing. Okay, although your rectangle is curved, but if you compute RU cross with RV, you are somehow computing the flat rectangle. Okay, flat rectangle means the parallelogram. Okay, do you see that this is not a rectangle because your line is like this? Not rectangle, right? Rectangle should be, I mean, at least parallelogram. You know how to compute parallelogram. Okay. You get what I mean? Okay. Yeah, we don't go precise into this definition. You can only get a concept of it. Okay. Yeah. Okay. Okay. Next. So you see, so surface integral here is what? We differentiate scalar field, okay, scalar field over a surface, okay. So this is a double integral here because we can reduce the rectangle from left and from right, from x direction, from y direction, and then every rectangle can carry a weight. Make sense or not? Previous is a line integral. Anyone can recall what's a line integral? What's line integral? Okay, I think a bit hard if I see this. So what is that? Zoom a bit. Yeah, so you parameterize your curve, right, using RT, and then delta T, okay, and then what else? Can recall or not? Recall the definition of line integral. Cannot? Go to the front. Compare the two. Okay, so here we have delta xi, the interval, and then I equals to 1 to n, and then n to infinity, right? So here we are cutting interval into smaller and smaller and smaller. Here we are cutting a square into smaller and smaller and smaller and smaller. But when you cut square, right, you can cut in two directions. Okay, UI direction and VI direction. Make sense? Okay, and then you have the same thing. Same thing. What's the same thing? They both carry the weight of F. Okay, they carry the weight of F. Okay. Yeah, one is line, one is surface. That's why they call lines integral, surface integral. Integral over line, integral over surface. Okay, line integral, surface integral. Make sense, huh? Okay. Got question or not? Question? Question? Okay, we almost want to go to the fun stuff already. Wait,
fun stuff 啊，你讲搬就不一定是嘛。
就不一定 fun. Okay, come. Next. Actually, you see. So similarly, here is defined using limit and sum, right? So this is not very useful. So what to do? We introduce a more useful formula here. So how to do surface integral? Okay, what you do is you have the Jacobian factor coming in. Okay, the Jacobian factor, which is the area of the parallelogram caused by the parametrization. Okay. So if you start with a surface, parametric surface, okay, then if you do the surface integral over F is the double integral on the function applied on the parametric surface and then multiply by the factor of the area of parallelogram. Okay. Okay. Okay, and then dA. Okay, dA is the one you know how to do because dA you go back to XY coordinate. You go back to the flat world. So if it is dA, you can apply the Fubini stuff. Okay, dx, dy, dy, dx, something like that. Okay, but if it is just ds, okay, if it is just dx, this x is curvy one. Okay, it's a curved surface. You don't know how to do. Okay, you need to make it back. Yes. I mean, hey, yeah, okay. No. I mean, that one is your own language. Yeah. So you turn it to your own language. Okay. So if your function can be written in z equals to fxy, then you can sub the area of the parallelogram as the square root 1 plus del z over del x squared plus del z over del y squared. Okay. So this depends on what kind of parameterized surface you have. Okay. Yeah. If you don't remember this, right? Don't remember the second one, it's okay. Just use the first one because everything can write in the first form. Okay. Even give you the second form, you also can write in the first form. You know why? You see, so this function is z equals to fxy, right? How do you write out the vector formula here? Vector function here. This vector function here is just what? It's just x, y, and fxy. Okay, and then you can just use this formula here. So the first one is the most general one. Okay, so you just remember one is enough. Okay, the second one is derived from the general one. Okay, can get it or not? So meaning if you go and do the tangent vector on two direction and then you cross product and then you take the square root square, then you'll get this. Okay, yeah. So just remember the general one is enough. Okay, area of a rectangle parallelogram is what? Is the tangent vector cross with another tangent vector and then you take the length. Yeah. So if the function is 1, you just compute the area of the surface. This one we go through just now. Okay.
Okay, so let's do one computation. Make sure we know what is going on. So compute the surface integral of x squared where x equals s is the unique sphere, x squared plus y squared plus z squared equals 1. Okay, so it says that do surface integral. So check first whether this x is a surface or not. Is this a surface? Surface, right? It's a sphere. Okay, sphere in R3. So this is a sphere. Okay, so the surface is the sphere. Okay, so the surface is the sphere. Okay. So this is the sphere. So what's the formula of the surface integral? Okay, so let's put here. So you want to see what happened to this graph or not? What happened to this graph? So you can't really draw the surface, the function, right? Can you draw it? Can't really draw it, right? You need to add another dimension to it. Okay. Otherwise, what you need to do is over every point, what is the value attached to it? Okay. So over every point, what's the value attached to it? X squared. Okay. So the value attached to it is x squared. Okay. So over every point, you have an x squared. So you need to sum all of them together over the surface. Okay. So you have a surface. Okay. Surface integral. What's the formula? Okay. How to make it into flat? Okay. Like Yi Zhao said, how to make it flat? How to make the spheres flat? Okay. How to make the sphere flat? What's the factor you need to consider? What's the Jacobian factor? The area of the parallelogram. Okay, so which parallelogram you are looking at is the r phi and r theta in this case here. Okay, why is it r phi and r theta? Because last time we already parametrized the sphere. Remember last time we parametrized every sphere already? A squared, right? Every sphere we already parametrized. Remember or not? Just 30 minutes ago. Okay, so you see, just now we parameterized every sphere already. This example here, we parameterized every sphere. Okay, in particular, this sphere is A equals to 1. Okay, so you just sub A equals to 1 here. Yeah. What? Yeah. So what's this parametric surface here? So my parametric surface is sine phi cos theta sine phi sine theta and cos phi. Yeah. And get it? Get it, huh? Okay, so from here you can compute your tangent vector at 2 directions. One is phi, one is theta. Okay. What's your domain? Domain is everything covered from 0 to pi and 0 to 2 pi. Okay, so what's the R phi? R phi is just, yeah, so you get cos phi, cos theta, cos phi sine theta minus sine phi. Okay, and then the other one you get minus sine phi sine theta, sine phi cos theta. The last one is 0. Okay, can follow up to now? Can follow? Okay, then the Jacobian factor is the length of the cross product. Okay, length of the cross product. So we need to first compute the cross product first. Okay, so what's the cross product? So this cross product kind of long. Okay, so this cross product here kind of long. Okay,
this cross product. Okay, so how to compute this cross product here? What do you get? Sine square phi cos theta, sine square phi sine theta, sine phi cos phi. Okay, so this is the cross product. So how to compute the length? They know how to compute the length. Length of the product. Length of the vector. Sorry? Square. Okay, you take the vector dot with itself and then take the square root. Okay, so you dot with itself, what do you get? Sine square cos theta square plus sine square phi sine theta square plus sine phi cos square root. Okay, so what are these? What you left with is just sine phi. Yeah, try have a look. Yeah. And mathematics is like this one. You go very complicated and suddenly come back very easy. If it still go very complicated, that is called chaos. Okay, chaos theory. There's some part called chaos theory. But usually mathematics is will get easy as possible. Huh? I don't know. It's like that. Because the nature follow the most easiest path. If it is too hard, then it cannot exist. Huh? No. I mean, yeah. Not necessarily. I mean, yeah. Right. Yeah, maybe I write one more step, maybe it's easier. Yeah, I think from here it's easier to see. Okay. Yeah, continue. So my double integral here become flat already. Okay, when this is flat, then we can use the technique from the flat case. Okay. So the flat case here is I substitute my x first. Okay, and then I multiply by the Jacobian. So what's the Jacobian here? Sine phi. So sine phi. dA. Okay, so what's the d now? What's the d now? What's the d now? Okay, the d here, we are integrating a sphere. Okay, but we turn it into a spherical coordinate. Okay, so what are the phi and theta we consider here? We consider phi from 0 to pi, theta from 0 to 2 pi. Okay, so the domain here is, okay, the domain here is 0 to 2 pi, 0 to pi. Sine cube phi cos square theta, dv d theta. Okay, so how to integrate this? You can also split the integral, right? Because the domain doesn't depend on each other, so you can split it. But there's a cube, right? Square, you just make it a double angle. But cube, what to do? Cube, wait, let me see. Let me see. Yeah, so this cube here, there's one technique you can use. Okay, so this one here, we just integrate 1 plus cos. So one technique we can use here is what? We can split up the sine cube. 1 minus cos square phi sine phi. Okay, so why do I want to do this? Because I can split one of them into sine. Okay, the other one is cos square times sine. Okay, why is this good? We can use the substitution, integration by substitution. Okay, so if you don't follow the computation, it's okay, but in the end, you will get 4/3 pi. Okay, you can try finish it. You will get 4/3 pi. Okay, use integration by substitution. Okay, before you leave, right? Let me show you something. Important. Not tips. Okay, not important, but not important. Important. But not exam stuff. Because this is the so for line, right? Okay, for line we have okay, so for line we have a loop, closed integral over closed loop, right? Closed loop. All right. So we need to consider the orientation. Okay. For surface integral tomorrow, is it tomorrow? Yeah, tomorrow we also will integrate over closed surface. Okay, like a sphere closed up. Okay. So we need to give orientation. Like what I said just now. If K is positive everywhere, then it is outward. If negative, it is inward. Okay, orientation of the surface. Okay, each point you need to give orientation because over the surface, right? There's a normal vector, either out, either in. Okay, you need to pick. Okay, if you pick all out or all in. Okay, but there exists a surface that has no orientation. Yeah, there exists a surface that has no orientation. So let me just close this up. And then on Tuesday, we will talk about again, but let me show you first before we leave. Oh, is it okay? Yeah, okay. So let me turn on, turn off. So, okay. So you see, can you see this or not? So this is a strip. Okay. So I draw a red line to go from finish one strip here. Okay, one round, and then green line the other round. Okay. Okay, these two. Okay. But there's a surface that's not orientable. Okay, how do I construct this surface? I take the other end and then I turn it and then I attach it. Okay. Okay. Yeah. Okay. So this is called a Mobius band or Mobius strip. So why is it not orientable? Okay, let me show you why is it not orientable. Meaning, if I put an orientation on one point, it is not compatible. So let me show you. So let's say, Jason, can you come help me take the mic or not? I cannot hold the band. Okay, thank you. Okay, thank you. So you see, let's say we want to put orientation on this dot here. Can you guys see this dot here? Okay, let's say we start with outside, and then I go along the strip. Okay, I follow the path. I go along the strip. Okay, I go along the strip. Okay. Okay. Can see or not? Can I? And then I haven't shown you one side. Okay, you see, I come back to the same point, but this arrow already point downward already. So there's no proper way to give orientation to this surface here. Okay, so this surface is not orientable. If you want, you can try and play with it. Okay, so you see, one thing to notice here is, you see, when I go through this strip, right? I go through the, okay, let me find the camera. So you see, when I go through this strip, right? Actually, what happened is you go from red line to green line. Okay, so you walk from the front to the back. Although you only look one round only. Actually, you go from the front to the back. Okay. Yeah. So just now you think that you only go around once, but you actually go around twice already. Yeah, you go around twice. You go inside one and the outside one. Okay, you go around twice. The normal circle. Okay. Yeah, this one is very advanced knowledge. Okay. Yeah. If you want, you can play around with this next week. Tomorrow I will bring this also. Okay, we will revise this idea again. Okay. Infinity? Not sure. Where's the infinity? I mean, 10, right? I go to the same point already just now. Yeah. Yeah. Same point on the plane. Same point on the plane. How to time travel this? Oh, that one is wormhole. I mean, if you consider these two types. Yeah. Huh? Non-orientable surface. Non-orientable surface.
还绕两圈套它，这两个。
Now wormhole